Hello everyone. I welcome you to the day 23 of the training, and I'm so happy that you have made this far by understanding all the lectures that you are going through till this day 23. And so far we have discussed about Verilog HDL modeling structure. We have discussed about behavioral modeling, switch level modeling, gate level modeling, data flow modeling, and with examples of Verilog HDL and implementation of the test bench simulations and understanding the architecture of the FPGA, how these designs work and how these are internally connected. We have introduced a finite state machine as well. In the same way, today I'm going to discuss about more about memory design. In the last class, we have introduced ourselves to the memory design, a smaller memory design, and today we will go deep into the understanding of memory designs, how they work, and how many types of memory designs do we have in the industrial applications in the real-time projects, so that you will be way more familiar with the memory designs, which is most essential part of any architecture. See, if you have taken any architecture of Cortex M0, M4, or ARM architectures, or Intel FPGA architectures, or any other architecture of a chip, the memory design is the most essential thing. And in that sense, let us go to the today's agenda, memory design. And one second. So today's agenda is memory design, understanding of the memory, and example implementations of the memory and RAM. RAM, SRAM, or we can call it as a basic random access memory that we want to read and write the process of the data. So that is the major application of RAM. And RAM is used for any operations, but ROM, read-only memory, is used for storing of the data of our projects, of our design modules. In some of the servers or the machines, we only store the data of intellectual properties. That's called read-only memory. I have given examples of read-only memory as SSDs nowadays, and RAM can be of your own piece of hardware on the motherboard of any device. If you take a laptop, you will have a RAM of 8 GB, 12 GB of different cores, octa-core, and dual octa-core. Now the generations of technology is evolving. Hence, that is our today's agenda. Let us go to the memory design. What is this memory design? Memories are generally considered as two types: larger memory block and minor or smaller memory blocks. Larger memory blocks are considered from the IPs, which are nothing but intellectual properties that we acquire from the different types of vendors. We have Mentor Graphics, and we have uh, Synopsys, we have Cadence, and we have Intel, which has different IPs for memory blocks, and Siemens EDA is one other vendor. So these are all the different vendor companies outside in the real-time world, which already designs, and the group of engineers already develop the blocks of design. Which, for example, if we need 8 MB of a RAM chip, that 8 MB of a RAM chip is already designed, and we can directly take it and implement in our FPGA chip development. So that is called IP integration. So we have done one project on IP integration as well. In the same way, these larger memory blocks are usually considered from the IP vendors. As I said, smaller memory blocks can be designed for the simulation purposes with two-dimensional array of the blocks. That's what we have done in the yesterday's class. Today we will be designing some other memory block items. Hence, our aim is to synthesize the memory block. I'll give you some basic examples of memory block, how you can easily describe the memory blocks of 2 KB, 1 bit memory, or 2-bit memory. Some basic examples. So how these memories of smaller blocks are designed. So those are designed with, for synthesizable blocks, we are using arrays of registers for the design of memory block. So these can be arrays of registers. So array is nothing but group of bits aligned. So in this bunch of array, in this bunch of bits are called arrays, and these array registers stacked up in a row, in a column, is nothing but memory. So that is what array of registers are represented as shown in below. Yeah, this one. So coming to the memory design, what are all the inputs and outputs that we should know? Now let us understand about the inputs, outputs of the memory block. Usually, as we have discussed in the yesterday's class, you can see that is address location should be there for each of the register, from which location you should be reading, or from which location you should, for which location you should be writing the data. So that address is one of the inputs. And data in, so we are sending the data in this way. So for that we need to send the data through one bus, and we need a clock for the design. Commands, we can have commands in this way, like write data underscore write, or data underscore read. Okay, so that read command is given as the signal, and write is also given as the signal. Clock is also there for memory, and you can also keep one reset here as a connection. So inputs, inouts and outputs are based on the read write operations of the memory block. Basic and standard thumb rule: usually in the memory we can read only, or we can write and read simultaneously. Remember this point and make a note of it. Either you can only read, like read only memory, from that memory you can always read, or you can always write. Okay, so that is the application. Now moving to the example, some basic example. Whatever might be the memory model that you want to write with group of inputs, this is the syntax you need to follow. As I have explained yesterday, this is nothing but number of bits per register. Okay, but this represents how many registers you should have. How many number of registers you are having. And for initialization, for at different address locations, so this is the address location. So at this address location, address of the array location, so this is the array, right? Register number of bits 0 to 7 is nothing but 8 bits. So 1 2 3 4 5 6 7, I mean 8, 1 2 3 4 5 6 7 and 8. Got it? So you are storing some data in it. For example, consider as 0 1 1 1 1 1 and 0 1. This is the data stored in this register of array. Array is represented usually in terms of register, like this. Okay, give a space here, and this mem of 0 or mem of 6 is nothing but address location where the data should be stored. So that data is stored in the 6th register here, like this. Okay, and end module. So just we are initializing that we have been storing the data into the location of mem0. So what are we exactly doing? Consider this as the information, that is data. What are we doing? We are giving this data to the some location called mem of 0 at 0th location. In the same way, this is the data, and this data is sent to the memory location of 6. Understood, guys? So that is the meaning of equal to symbol. RHS value is considered into the LHS value. So what are we doing? We are sending data to mem. So we are writing, actually we are sending data to the memory. So we are sending data to memory location. For example, if it is 0, 1, 2, 3, 4, 5, 6. What am I doing? I am writing data. I am sending data through data bus and to the location number 6. And in the location 6, what data I have stored? 4 ones and 0011. So I have stored 4 ones, 1 1 1 and 0011. This is the data I have stored. So in the location of 0. So this represents mem of 6. Likewise, mem of 0 is represented like this. And mem of 2. So what is mem of 0, mem of 2 and mem of 6? Those are nothing but locations, location representations. Okay. And in this location number mem of 6, location is nothing but address 6. We are writing data like this. This data is written. That is the meaning of this entire thing. Keep it clean. Okay. So I hope you have understood this thing, irrespective of inputs and outputs. Let us go to the next thing, initializing memory block. How did we initialize the memory block? Here, for initializing the memory block, you can see read operations. This means assigning the values or information data bits to each array among 1023 registers. So 1023 registers or 1024 actually, starting from 0 to 1023. And what does this mean? So group of registers are there. For that group of registers, I am writing data to each one of these. That is called initialization. So here for initialization, you can see read operation. This means assigning the values or information or data bits to each array among the registers. If you have 1024, absolutely fine. And reading file data is done by the system task called read mem b or read mem h. B is binary, h is hexadecimal. No big difference, but the syntax $read mem b or $read mem h is nothing but reading file data, and it is a system task. Reading file data is nothing but you should mention the file name or location of the file from the project directory. As I have said, if you have C directory and you have memory design, and in that you have stored input.txt file as an input, that should be mentioned in this way. And next you have to name the array, name of the array. So you have to give the location, like name of the array represents the the which array among a memory block is called for read. So if you have mentioned the array name, for example, usually we can see array name as register here, or you can see array as ARR, and so that you can name it as ARR, and for that ARR, name of the array represents the which array among the memory block is called for read. Is called for read means from this array location your data is read, and you have to mention start address and stop address because you have 0 to 1024, right? If you don't mention start address and stop address, all these 1024 locations are accessed and all this data is printed. That is the meaning of read. So it is read to the output. Else, if you have mentioned from 5 to 10, only 5 to 10 data locations are accessed and the data can be read. So there will be a little delay if you have not mentioned start address and stop address. All the address location data is printed. So in order to avoid it, it is better to mention these locations. So that is it. That is the syntax for initializing the memory block. Now come to the example for initialization. For example, you have a memory module and register mem you have mentioned 0 to 1023. So you have 1024 locations of address or 1024 registers of arrays. Okay, 1024 registers of arrays. Initial begin read memh mem.dat, that can be your file name, and mem is the array name of array, that is mem, and start address is 500 to 80 is the end address like this mentioned, and you can end and end module, that is written in the initial block. This is initial block. Okay, so that is about initializing memory. Now let us develop the design of synchronized RAM design. What is synchronized RAM design? So in this synchronized RAM design, take module RAM underscore mod, and you have to mention what are the inputs. Inputs as address, data bus, clock, read and write signals, and chip select, CS. So selection inputs, which is nothing but for any memory inside the selections of this data reg or input arrays, those are selected and in the initialization. And after you mentioned, after declaration of the first step, this is the second step, input. What is the input? Input is address with 10 bits because we have 1024 registers. So that number of you start with 0 and you end with 1023. That is what this address location is called. Okay, here the initial address is always set to 0 and your data went through this thing. And how many values of the address location you have? Address 1 is nothing but 3, 4, 5, 6, 7, 8, 9, 10. So you have 10 bit of address locations, you can see. And in out data bus, you have to give the data bus as well. You can see the data bus, in out data bus. And for that, you can see reg, where is the cursor? Yeah. Memory is memory declaration of 2 power 10 arrays of registers is mentioned here, and one thing for the output is data out. You have data in as the data bus, and you have data bus. Let me mention data bus, and the output is data out. And assign data bus is equal to CS and read, because chip select, when you select this memory, that is okay, that should be true, 1, and read should be also 1, Then if these both are true, you can send the data to data out. So whatever the data out consists data, that data out can be taken from the data bus, or data bus condition is assigned to data out. Or else it is a open, high impedance, else high impedance. Always at the rate of posage clock. Synchronous means it is considered with the clock. It is relying on the clock, posage of the clock. If chip select and write and not read, this is write process. Write process. This data bus is sent to memory address. Which location? So from this data bus, some of the memory location is accessed now, and for that mem of address data is sent. Always at the rate of posage. If this is not the condition, if in the read process, from the memory location, you can see the data is sent to the data out. So into the data out. Okay, data out is a single unidirectional, and it is just like what is the output? That is just a register here. So there is no harm in using the data out in the always block, in the procedure block. If it is an in out, see, we have ignored data bus. Here. Memory address cannot be sent to data bus because data bus is a in out. So bidirectional, it is better to avoid. It is mostly avoided in the procedural blocks. Asynchronous, it is nothing but it is based on the inputs. That is the major difference between synchronous RAM design and asynchronous RAM design. You can see everything is similar. So everything is similar in the terms of code, but whenever the write and read process is happening, this is read process, this is write process. Entire structure is same, but write process is happening when address, data bus, read or write or chip select is happening at always at the rate of inputs. If chip select and write are true, that means they are 1, they are enable, but not read. But for this read process, read should be enable, write should be not enable. Okay, so else the remaining is same. Understand the basic difference. Then coming to the in out. Now I'm just summarizing the in out. Why don't we use this in out declaration in the database? In out declaration of the variables is mostly avoided because of tool based inconsistency while execution. There will be a conflict while in terms of execution while in the EDA tools. Hence, also note that in out variable cannot be declared in the procedural blocks. Just remember, we haven't used data bus input wire or in out wire. That data bus variable or the register or the wire is not used in the read process, in the procedural read process, because execution inconsistency. How can we resolve this in out data bus issue? Like, it is a bidirectional, right? In out is nothing but it is a bidirectional. So how can we resolve it? We can resolve assign data bus into chip select. Assign data bus is nothing but assign value of data bus, which is in out. And for that, if read is equal to 1 and chip select is 1, if both are 1, that is true. If you consider both of them in the read process, then let me take another line. then data out is assigned to data bus. So data bus is equal to data out. Okay, if not, it is open. Data bus is open, high impedance, no value, not considered. So in the always at the rate passage clock, what you are using, instead of data bus, you are using data out from the memory location. So from the memory location, what are you doing? You are reading. This is a read process. Hence, read is enable, chip select is enable, write is not enable. Write signal. These are the command signals, okay? Those are the input signals, command signals. So that is the declaration. It is a most important point to be kept in mind in terms of design, any design. So in out usually is not considered in the terms of procedural blocks. Okay. To resolve that, we have used this kind of operator. The one single in-out data bus wire is now split into two individual data in wire and data out edge. So this is the solution for bidirectional data bus into single directional data in wire and data out edge. So this is the memory. So that is the data in, and if this is the write and read buffer, tri-state buffer. So what are we implementing now? We are getting a solution for using bidirectional data bus wire. This is a bidirectional data bus wire. You can use it, but instead you have to implement one set of hardware in one step for write and read process. In the tri-state buffer, what it is done? It is doing that data in, data sending into this. So it is write, and data collected from it, from the memory, it is read, is sent to tri-state buffer, and tri-state buffer is connected to data bus, bidirectional, and this bidirectional can be connected to some other module in the architecture. Understood my point? So this is how you can resolve the bidirectional issue as well. Okay, that is what, this is another solution. So keep in mind, what are you doing for the mem? You can assign a tri-state buffer for data in wire and data out register. Okay, so this is it, and let us go to the example of memory design with the same implementation as RAM underscore modeling. And for this design, now we are implementing some set of parameters, address size. It is a typical representation in the larger Verilog HDL codes. Usually you cannot write this parameter, but if you write it, it is used in the whole bunch of Verilog HDL file. So imagine for this module you have an extension module, and for that extension module you are using this address size again in the next extension Verilog file. So as a common terminology, you can represent in terms of parameter. It is a best practice. And for the inputs, data in and data out, address, write signal, and CS, we are writing the data now. Word size is 8, so that is nothing but in the data information, if this is the array and you have 1 1 0 and 0 0 1 1, so you have data of 8-bit, and for that 8-bit data, that is the word size. Memory size is 1024 as you have asked for. 1 kilobyte, it is nothing but 1 kilobyte. 1 kilobyte is 1024 bytes. Bytes is nothing but 1024 bytes. And how are these bytes represented? In 1024 locations, starting from 0, 1, 2, 3 and so on. 1024. Got it? So in this number of bytes, each location has each thing. Got it, guys? This is the simple representation, and after that you have to mention input and output, and this is a representation in terms of parameter. Good representation. You can see the bar. Earlier we used to write 7 colon 0, right? Now that 7 is represented like this. Okay. And data in, write and CS chip select and write signal. Output, we are writing data out, output as data out, and register. Mem is represented in this way, like, one second. Mem is represented in this way. This is 1024 minus 1 colon 0 and 8 minus 1 colon 0. What is it represented? 7 colon 0 mem and 1023 colon this thing. This is represented like this now. Don't get confused, guys. This is new type of representation, because if you learn these methods in an advanced way, it will be very unique when you have asked for writing a memory design in the interview. In the interview, you can be way ahead in writing this kind of generalized and way more advanced kind of thing in the EDA tools. So from that syntax and that kind of nomenclatures you can use. So best practice, and assign the data out like this to the memory address. So whatever the memory address you are having, that is read into the data out, but always at the rate of write, and this whatever the data is getting here, that can be sent to the memory address location. So from this you have data in, and from memory you have data out. So this is mem. Okay, in particular location at address, at particular location of the address, you are taking the you are sending the data into it. That is the meaning of from data into the memory address location. Now from this you can directly access to the data out without any temporary registers. See, I haven't mentioned any temp, or I haven't mentioned any data underscore reg. You might have remembered from the previous classes, data reg as temporary registers. This is how you can solve the bidirectional data bus issue, like in-out issue. You can solve it in unidirectional, and that unidirectional registers data out, output is register, inputs are wires. So those kind of registers can be used directly. Okay, so that is a design. For that design, if you want to have a test bench written, this can be the test bench, and that test bench starts with tick timescale, this tick timescale, and module ram underscore tb, and whatever the wires in the design, that can be registers, and registers in the design that can be register for the only for the memory, remaining all altered. So by this time you will be very familiar with the test bench as well. So ram underscore mod dut initial begin. Now let us start with the for loop, and for the for loop initial k, integer k, what are we doing? We are having the data in at different locations. So k plus k percentage 256, that location we are getting, and that from that we are accessing the data, and now it is write enable and chip select is also enable. After 2 nanoseconds, write is 0 and CS is 0. So now you have a data now. Some operation. After this operation, some data in has some information. Data in has some information. Else end. And now that K is also used again. Where are we using in the data in? Where for every 1023 locations, you will be using the data in. And repeat this process for 20 times. For the 20 times. Repeat 20 is 20 times. And begin after 2 nanoseconds. Address is random myseed. Myseed is nothing but you are using myseed integer to get some random value. Let me give a random value of 1000. Don't get confused. A random value of 887. Okay. For that random location, for the $random myseed is nothing but for that random location and random value, some random value, and that is percentage 1024. You will get a reminder. Percentage meaning is nothing but reminder, and that reminder is sent to the address. Okay. Now write is 0, chip select is 1. Display the address. First, just display the address. Address is nothing but percentage 5D. Address is 5-bit, right? 5-bit decimal, and data is 4-bit decimal. Address and data out is mentioned. So data out is mentioned and address is mentioned in this percentage 5D. This is how you can print off the display. And end with the begin, and this end with the initial begin. For the value, you can see myseed is 36 I have given here instead of 887, and for that you can see dump file and dump wares are for the output waveform generated. So this is how you can write the test bench for memory design of 1 kilobyte with the solution of bidirectional and read and write process. So here the data in has written into the data in, and that data in can be used for memory address. In the test bench, whatever the data in we are acquiring from this, k is equal to k plus 1 increments, for everything increments. So that data is connected to here in the design. From the test bench, it is connected to design, and that address location is operated. If write is equal to 1. So if write is equal to 1, what are we doing? We are assigning some value to data in. You can simply give for data in as a normal value, but we have 1023 locations. So for that 1023 locations, we have to write all the data here for every location. That is the reason we have used for loop. And be careful with the begin and end every time. Don't get confused. Okay. And initial myseed, we have assigned value as myseed 36. You can give any number. You can give 887 as well here. And initial begin, dump file and dump files are nothing but output waveform generations. If you are new today, this is a simple example. And how do we look into the waveforms? Some random values are generated. All the inputs and outputs are represented here. Address, 10-bit address location, and chip select. Data in and data out are the input outputs. K is an integer. Mem is our memory. That is memory. Entire memory is full. Hence it is represented in this way. Entire memory is full. Now myseed, what did we give? We have given some random value. 24 is represented in this hexadecimal. So that value. Write is 0 until this point, until some till what point? Till some point of the time write is 0, then write is 1, I mean right is 1 and then right is 0. The cursor where I have pointed this cursor line, like this cursor line is representing the 0 value. Okay, so at this point you can see my seed is 0 decimal 5. Okay, you can see the mem completely full, and data in, what is the data? F2, F4, F6, F8, FA, C, E. That way the data is written, and address locations 200, 1, F8, some hexadecimal represented. This entire radix is in hexadecimal. So for your ease of writings, I have made this design and test bench screenshots kept aside one by one, you can see. And then that is today's lecture. And in the kernel, in the terminal window, in the EDA playground, you can see the data. Address is 512 and data is nothing. Data is some random value. Don't care. Whatever the data you are writing, it is don't care. Some X value. It is not mentioned. That is what is represented here. X value. Don't care. So it is full. Some random data can be written here. Not an issue. So that is represented in this way. For each and every address location, that's what we are printing now. Here it is printed. Address is and data is. From the data out, you are getting data in, and address, it is this. Okay. So we are not giving any input file. We are only giving data generation into the data in. Okay. Hence that is this, and this is a static RAM. That RAM application of 512 kilobyte, we have just made 1 kilobyte. For 512 kilobyte, you can work on it. You can make your own design of 512 kilobyte. So what should be the size? Think of it. Think of the remaining sizes. Change them accordingly. And now that is SRAM. 8 megabyte HD RAM, static dynamic RAM, and all these IPs. These are IPs usually. These are the larger, complicated, larger memory designs, and these IPs are obtained from some vendors, IP vendors. So that is my point here. Some smaller blocks, smaller memory blocks, we can design. That's what we are simulating here. Smaller designs. Okay. So that is it. If you have any questions, please let me know. I'm happy to answer. And thank you so much.